Hello and welcome. I will talk about a few different challenges on mammography. So I will start to talk about uh, challenges on mammography measurements in general. Then we will go through how the X2 MAM and RF sensors are designed to cope with these challenges. And finally, take a look at some measurement examples before answering questions at the end. So, mammography machines compared to other X-ray diagnostic imaging machines face some additional challenges when it comes to non-invasive measurements. We'll look through some aspects of this before we start looking closer at the RaySafe X2. So, history of mammography. For many years, analog mammography was more or less the same. Machines were using molybdenum target on the X-ray tube, and you were running 20 to 35 kV with molybdenum filter at the lower end of the spectrum, and using higher energies, you were using rhodium filter. With the digital revolution came a lot of new challenges with mammography. The digital revolution has resulted in new target filter combinations, new acquisition modes, and a lot of behaviors that we never saw before. So measuring on all these variations can be a huge challenge. There are different types of challenges, but here are things that can be model specific. You have anode angles that can vary between machines, can have different anode materials and purities. The tubes can be mounted on different angles. And then we come to filters. The filter can have different materials, different thickness, different purity, different homogeneity, and it can be placed on different angles between machines. On top of this, we have the compression paddle, which can be there or not be there. And on one and the same machine, you can have 9, 10 different paddles, and they can all have different thicknesses. What we usually in this segment use to express this is the target filter combination. But as you can see here, there's a lot more to it than just the target filter. These variations adds to the complexity of these measurements. On top of this, you have individual changes on the machine, and they can happen over time. So tube aging, for example, it results in reduced output of the intensity, and changes the X-ray spectrum as well. So when the anode surface becomes a bit rough, you get increased HVL and reduced dose output. You have the same effect with filter corrosion. Not all materials corrode, but some do. And when that happens, you have the reduced output in intensity and change of X-ray spectrum again. Acquisition modes. So the typical standard acquisition modes that we have seen for so many years is the 2D or two-dimensional exposure. Single exposure, one pulse, or a flat image. Other examples are tomosynthesis, where you take a number of exposures with different angles to build up a 3D volume. This can be a small movement of plus minus 7 degrees or a large movement of plus minus 30 degrees. And you can have a combination of acquisition modes where machines vary the filter material, change the kV, and change the pulse behavior in the same exposure. And then we have sensor positioning. The small geometry of a mammography machine makes it difficult to do high precision dose and HVL measurement because of scatter. Scatter can come from examination table. It can come from the compression paddle, and it can go up back, can come out from the collimator, and it bounces back and forth. What should be measured is dose free in air, RaySafe, or whatever name you have on it, but the measurement should not contain the scatter. But a traditional ion chamber registers radiation from all directions, so it's impossible to place it free in air because of the short distances. This is a huge challenge for instruments to sight. Sensor positioning again, Hill effect and inhomogeneous fields. The built-in Hill effect of an X-ray tube is in mammography used to its maximum. The dose is the highest at the chest wall side and can be 25% lower. The benefit of the Hill effect is to compensate for the breast that is thicker close to the chest wall side and the other side. The challenge when measuring is that the exact positioning of the instrument becomes very important to be able to compare data and to know what is measured. You have the same but opposite effect, the HVL. So, reference position for dose varies around the world. IEC and EUREF say that the dose position should be at 6 centimeters from the chest wall side and 4 centimeters up from the examination table. While in US, ACR says you have to measure 4 centimeters from the chest wall side, and the dose reference position is 4.5 centimeters up. The dose measured at a different height can be recalculated using the reverse square law, but the distance from the chest wall side has to be at the reference distance. It's not really so easy to recalculate afterwards. Tube voltage. So ZKV affects the X-ray spectrum, but what comes out of the X-ray tube and can be measured in the radiation with is radiation with a spectrum of photon energies. What the spectrum contains is affected by all the challenges we have already discussed, but also by the set KVP value. KVP cannot be read directly from the radiation, but if other variables are known, the remaining effect caused by the KVP setting can be determined and calibrated as KVP. But this is not as straightforward as dose and HVL. Summary of these challenges is we have model-specific challenges, which gives large variation of target filter combination and paddle options. We have individual changes over time, which creates unexpected variations in beam quality. We don't know what we can expect. We have acquisition modes. Again, variation in target filter combinations over the exposure and pulse sequences in the same measurement. We have the sensor positioning, the scatter, the Hill effect, and the reference position, and then do voltage measurement, which is only possible if all the other variables are known. Okay, so this was the first section, and now we would like to know a bit more about you. So I would appreciate your input on a couple of questions. The texts of the replies will be presented during this webinar, and individual replies are anonymous. I'll give you a couple of seconds to find how to reply, and then I'll continue while you answer the questions. Chapter. We have talked about challenges with measurements of mammography machines, and now we start to look at the X2 system and how it handles these challenges, and specifically the design of the X2 MAM and RF sensor and how they are able to measure the different parameters. The RaySafe X2 system is the standalone measurement system. There is no selection of sensors or modality types. It's just to connect the sensor and start measuring. We get all parameters in one view, including waveforms. X2 automatically stores everything as you measure and works plug and play. You can connect wirelessly to a PC and Excel for live export of measurement data while you're measuring, or you can upload the measurement afterwards from the instrument for export or storage. So the following presentation will focus on the X2 MAM sensor. So here are the physical properties of the X2 MAM sensor. The active sensor area, and you don't typically find this in the specifications, so it's 4 by 9 millimeters. Both MAM and RF sensor measures within specification for a span of plus minus 10 degrees in both directions, while the MAM sensor has an expanded angle of plus minus 30 degrees in one direction, and this is to be able to handle large tomosynthesis movements. The reference height is 7 millimeters, the reference height for dose, that is. What you see on this slide is the MAM sensor cut in half. The radiation sensor consists of 4 diodes placed on top of each other. This gives us 4 signals for one exposure. The sensor is shielded from scatter by a tin cage with an opening on top. This makes it very insensitive scatter and disturbances. We only see the radiation coming from the tube. This design makes it rotation independent for any inhomogeneous fields, and it gives us true air karma as placed free in air, even if geometry is small and a lot of scatter. So this makes the impossible possible. So, dose. How do the X2 MAM sensor measure dose? To begin with, we use one sensor for dose on all target filter combinations and for all positions, with or without compression paddle, in front of or behind a phantom. And the sensor requires no settings for correct dose measurement. The measurement principle for dose is that it uses the top diode for the signal, and then it's using the remaining bottom diodes for energy corrections to give a very flat energy response. HVL. The X2 MAM sensor can measure HVL with only one exposure. In one exposure, you get 4 signals, again, with different filtration. So it eliminates uncertainties of variation between exposures, and because of the scatter protection, the HVL is measured as if free in air, even though it's in a confined space. This sensor measures one-shot HVL within 5% uncertainty for all existing target filter combinations without any settings or corrections. So true plug and play. How the Extremum sensor measures KVP. As mentioned earlier, KVP doesn't exist in the radiation. When we combine several signals and adjust for model-specific properties of the mammography machine, it is possible to measure KVP. From what the sensor does to what you do as a user when using an instrument. So, for dose on HVL, what do you need to do? You position the sensor, you do X-ray and take a measurement. That's it. No settings, no nothing. Just plug and play. KVP. You do one setting. You have to select the KVP mode. So you have a setting for which machine you should measure on. It's expressed either in target filter combination with or without paddle, or target filter combination with a specific brand name behind it. So select the KVP mode, position the sensor, do the X-ray, and you get the measurement result on the instrument. It's that simple. One extra note about tube voltage above 40 kV. Some machines have optional dual energy or contrast enhanced mammography functions. This is two exposures, one with normal settings and a second with high kV above 40 and high filtration copper or titanium filter. This second exposure is either tungsten copper, moly copper, rhodium copper, or tungsten titanium. For KVP measurements above 40 kV, use the extra RF sensor instead of the MUM sensor. There's no settings for that, just plug and play. Summary of sensor design. It's one sensor for all dose and HVL measurement in one shot, plug and play. The sensor and the instrument is developed for all existing mammography machines. It means any acquisition mode that exists, plug and play, check stop delay settings for desired behavior. Any target filter combination, plug and play. Any state of tube aging, just plug and play. It has capability to measure non-invasive KVP on all existing mammography machine, however, not on all beam qualities. The system can collect all your measurements without need for a PC. It's a standalone system, but it can connect wirelessly to a PC or with a cable for live export of measurement data during measurement or after measurement. Mammography coverage table is a list of validated machines that you can find on RaySafe.com. This list has a lot of dots. It's a list of the manufacturers and the model of machines, and it's a list of our different mammography sensors. So a black dot means it can measure kV, dose, and HVL, and a ring or a white dot means it can measure dose and HVL, but not kV. But as I said, we do cover all machines in the whole kV range for all of them. But if you run into problems when you're measuring, you have questions, you're welcome to contact our technical support at technicalsupport@raysafe.com. So now we would like to present the replies of the question we sent out.
Yeah, So the first poll question was, in your current role, do you perform measurements on mammography machines? 13% answered, no, I'm here to learn more about mammography. 8% of you answered, no, I'm here to learn more about the X2 system. And 36% answered yes. So then 42% did not answer.
So I hope that at least, I hope this could be useful for all of you. Now we'll take the second question.
So the second question is, if yes, what brand of mammography machine do you primarily measure on? 21% on Logic, 9% on GE, 9% on Siemens, and 7%. But not many people did answer this question. So Logic.
Okay, so interesting. So now we will take a bit look on application and measurement examples. I do this when rounding up the webinar with this. So starting with looking at the X2 user interface, this is what the X2 looks like after a measurement. You see 7 measured parameters, and behind 2 of the parameters you also see a blue line, which is the waveform, in this case for dose rate and for kV. When exported to PC software, these waveforms can be seen in the same graph. So I'll have one more slide before we start to look at the measurements. But measurement data can be wirelessly or via cable exported to PC software and to Excel templates. The X2 MAM has settings. There are settings, but the settings tailor how to view your measurements. So not the accuracy of the result. So stop delay setting. Change how data is presented, either as a row of pulses in one measurement, or it gives you each pulse as a separate measurement, where all the numbers you get on the parameters becomes for each pulse. So you can slide, once you hit stop delay, you can slide the number down to 0.2 seconds or up to quite a high number. In this measurement example, we look at measurement from a Siemens Mammoth inspiration. Not a lot of you had the Siemens machines to measure on, but I use this as a fairly simple example. Waveforms are often underestimated when it comes to understanding a measurement, but it's critical to understand the behavior of an X-ray machine. So here we first see the pre-pulse for the AEC. Then the machine calculates the settings for the main exposure, and it takes about 900 milliseconds. Then comes the main exposure. And I've written main exposure part 1. And then it's a break. This break is for the grid to change direction, because the grid has moved to its end movement and now it needs to change, so it stops the radiation, and when it's sped up in the other direction comes to the remaining of the main exposure. Now we see this as one measurement because the stop delay setting was longer than the longest break between 2 pulses. So here is the line per millisecond, and then we have 250 milliseconds. So if we instead now do a very short stop delay setting of 0.2 seconds and one exposure on the X-ray machine. Oops. We get one measurement with the pre-pulse. kV, HVL, and dose for only the pre-pulse. We get the first part of the main exposure, again, kV, dose, and HVL for only that pulse. A separate measurement at the end for the remaining part of the main pulse. So this was the simple example. If we now take a look at the Hologic linear dimensions in combo mode, where we have 18 different pulses. We first have pre-pulse for the AEC for tomosynthesis. Then we get 15 pulses with during 2.5 plus minus 7.5 degree movement. And then it's a break for almost 5 seconds, and again comes an AEC pre-pulse for the 2D exposure and the main 2D pulse. This is possible to capture in one sequence because of the stop delay setting of 5 seconds. Again, if we do a 0.2 second stop delay setting, all these 18 pulses would come up as 18 separate measurements. So it's a way to present it, but it's also a way to find out what the X-ray machine does. Additional X2 sensors for mammography applications. So I will just mention these two. So the X2 Lite and the X2 Survey sensors. The X2 Lite sensor is designed for calibration of medical monitors. It's a reference class contact light sensor with capability to measure ambient light. You can use it to check or calibrate DICOM grayscale standard display function, and you find the X2 Lite as a choice available in the Barco and ISO's calibration softwares. You can connect the X2 base unit to the PC where the calibration software is run. The X2 survey sensor can be used for tube leakage and checking scatter in the room, and it's a good tool to teach the staff working in the mammography room what have the difference standing behind the protection screen versus being in the room when you're measuring. Okay, so to summarize this whole webinar, measuring on mammography machines is challenging. X2 minimizes these challenges by being plug and play, being easy to position, and being having all data available for each measurement at all time, and with the fact that it supports all machines that exist on the market. This slide concludes my presentation, and we're now over to questions.
Thank you very much, Anders. So now we'll have a Q&A session, and we have gotten some questions from you already, but please feel free to type in more questions under the Q&A in the WebEx. So let's start, Anders, with some questions. We got one here that says, there is no kV mode for rhodium or copper. So how can kV be measured for these inequalities?
So for rhodium, the same machine also have other beam qualities where you can measure kV. So measure kV on a beam quality that is available, and when you're in rhodium mode, stick to measuring dose and HVL. If you set the same machine in only rhodium, you can run the same kV range. When you switch to rhodium copper, that only happens over above when you're above 40 kV, so you can use the RF the extra RF sensor to measure kV on that. And that works plug and play.
Thank you. So we have another question. Does a paddle in the beam affect HVL measurements?
Yes, it for sure. And it's easy to think that a paddle, one paddle is the same as the other paddle, but yes. When you want to measure, use measurement data to calculate AGD or MGD, you need to take the HVL and dose measurement behind the paddle.
Right. So we also have a question that says, can you make your slides available after this WebEx? And yes, we will share these slides on our website, and you will also get a link, dear attendee, to
everyone who attends the webinar gets a link to the webinar, and you can look through the webinar itself.
So we had a question that said, did you say that the X2 mem was independent of the 6 centimeter or 4 centimeter precision from the wall side? That's not correct, is it?
So, well, that's a tricky question, because when you measure dose on HVL, the X2 mem sensor will measure correct dose for the position where it's placed. But you should measure at the correct distance. So whether you measure on 4 centimeters or 6 centimeters, the sensor measures correct. But to capture the right dose for what you need to know whether you should measure on 4 centimeters or 6 centimeters.
So why is there a special setting for the Pristina?
Okay, so GE made a little twist on the new machine. They decided to add more materials in the beam. So you have a moly filter, but then they have added more plastic in the collimator output that offsets the X-ray spectrum to the point where we couldn't measure correct kV with the normal moly settings. So we needed to add a separate one for the Pristina.
Yeah. And then we have a question from the audience. I struggle to measure a kVp on fine focus. Any tips for that?
So one thing that we haven't said under challenges are that the sensors are calibrated for kV measuring on the examination table at 4 or 6 centimeters. What happens when you put the sensor on the examination table is that you change the dose rate. The machine goes down to maybe a third of the MA, so the output intensity of the tube goes down quite dramatically. It's a little bit compensated by the fact that you move closer to the tube, but you also need to remain with the same input angle of the tube. So if you measure on 6 centimeters on the examination table and move it up to 6 centimeters on the magnification table, you have changed the input angle from the tube. So how much filter you go through with the radiation before it hits the sensor and things like that. So if you can remain with the same geometry, you should be able to measure correct kV on the magnification table.
So you would need to take the angle of radiation into account and then calculate how to decrease distance from it accordingly.
It's exercise in geometry.
Exactly. So we have another question that if I have a 5-second exposure and my stop delay is set at 4 seconds, does the sensor stop measuring? Should the stop delay always be set longer and single exposure time.
So if you have one pulse that is 5 seconds long, the instrument will measure regardless of your stop delay setting. So the stop delay setting is only how long the instrument waits after the end of the radiation until it finalizes the measurement.
Yeah, we have questions coming in. It's great. Thank you so much for being so active. We have another one here. Your presentation indicated that dose should be measured with the sensor positioned parallel to the chest wall, and KVP and HVL measured with the sensor perpendicular to the chest wall. But a later slide showed the HVL and dose being measured with the sensor perpendicular. So could you explain this a bit more, Anders? What do we mean with that?
Or maybe I didn't do the slides correct. So the sensor can be positioned in any direction as long as the sensor area is on the correct distance from the chest wall side. It doesn't matter in which direction the cable points. It's independent of sensitivity to heel effects and stuff like that. So you can place it on the machine in any direction you want, as long as the center of the sensor area is on the correct distance from the chest wall side.
So I think what question might be referring to is that we showed that if you measure dose and position the sensor along the chest wall side, you have a 30 opening angle.
Okay. So yes, when you do measurements on tomosynthesis machines that has a movement that is larger than plus minus 10 degrees, because within plus minus 10 degrees, as you have on logic machines, you can place the sensor in any direction you want. But if the movement of the tomosynthesis is more than plus minus 30 degrees, 10 degrees, I mean, then the sensor needs to be positioned so it can take up the dose from the whole movement, which means place the sensor along the chest wall side.
Great. So it's only when you have tomosynthesis or large angles that you need to put the sensor in a specific manner.
Yeah.
Otherwise, you can put it anywhere. Great. So I think we will finish this webinar with a final question. So for KVP measurements, how does the sensor know the model-specific properties of each machine?
Yeah, it doesn't. That's where you come in as a user. You have to help the instrument by telling the instrument which KVP mode you want to set. So you select the KVP mode, and based on your setting, the instrument assumes that this is the machine I'm measuring on, and it's giving KVP from that. Did I confuse things enough?
Probably. Well, thank you very much, Anders, for answering all of these questions. I think that with that, we will end this webinar.